Hello, everyone. We're going to complete lesson 7, which is an introduction to the central limit theorem. So central limit theorem is a very important concept that we're going to learn about that basically is like the backbone of a lot of the statistical things that we are going to do later on this school year. So recall that a parameter is a numerically valued attribute that describes the distribution of a population. A statistic is a numerically valued attribute that describes some characteristics of a sample. So I like to remember this as P for parameter, which represents a population. So that means that if I give you a mean of a population, that is a parameter. If I give you a standard deviation of the population, that is also a parameter. S for statistics, which is for sample. So if I give you the mean of a sample or the standard deviation of a sample, that is a statistics, not a parameter. So more often than not, the value of a parameter is usually not known because we cannot examine the entire population. However, the value of a statistics can be computed directly from the sample data. We often use a statistics to estimate an unknown parameter. So for example, if we choose students from LPS to complete a survey, this would be a sample of the entire population of schools in the Bay Area. See, so a sample is taking from the population. So how good is a sample mean x bar at approximating the population mean mu? After all, one random sample will have a mean that is different from an independent second random sample. So what this part means is that the mean from one sample is different from the next. Okay, and we're going to do a simulation after this lesson that will make you understand this a little bit better. This basic fact is called sampling variability or sampling error, the variability we expect to see from one random sample to another. To make sense of sampling variability, we will look at a distribution of infinitely many sample means to try to see what the mean mu should be for one population. This brings us to the central limit theorem. The central limit theorem, CLT, states that the sampling distribution model of a sample means from any random sample is approximately normal for a large sample size, and we want to have the sample size to be about 30 or more. If the assumption of an independent random samples are met and the sampling size is large enough, the sampling distribution of the sample mean is modeled by a normal model with a mean equal to the population mean and a standard deviation equal to sigma x bar of which is equal to sigma over the square root of n, where n is our sample size. The concept is the most powerful concept in all of statistics. We collect a representative random sample and calculate its relative sampling distribution. Then we can make generalization about a population without knowing the parameters of a population. So we're going to go ahead and skip this simulation. You're going to actually do one later using this a worksheet that I provide for you. Okay. So let's say that we know that a population is normally distributed. This means that the sampling distribution, so if I was to create a distribution of taking a bunch of samples from this population, then mu of x bar is going to equal to mu, and sigma x bar is sigma over square root of n. So a sampling distribution is when you sample from the population. So think back to when we did the crazy in love activity. Every single time y'all calculated a dot, that was a sampling mean, right? You're taking individual means every single time. And then we created a distribution with the dots, so that was a sampling distribution. We also know that the shape is going to be normal, because if you have a normal population, your sampling distribution will also become normal after infinitely many times. If a population is skewed, uniform, or multimodal, meaning that it has many peaks, the sampling mean will be equal to the population mean, and the sampling standard deviation is sigma over square root of n, where n must be greater than or equal to 30. Once n is greater than or equal to 30, it will also have a normal shape. This next page shows you that as n increases for each of these different sampling distributions, eventually, once n gets big enough, the sample becomes normal. And you're going to see that occur with the simulation that you're going to do later on with the worksheet. So let's go ahead and complete this check for understanding. The height of male students at a local high school follows a normal mean of 68 inches and a standard deviation of 3. A random sample of size 10 are being taken for this population, and their mean height is being calculated. Describe the sampling distribution of the sample mean. So we know that it's going to be normal, considering that the population was normal. We know that mu of x bar, so the sampling mean, is going to be equal to the population mean, which is 68. We know that sigma x bar is equal to standard deviation over square root of n, which is 3 over the square root of 10. So this is describing the sampling distribution. Which of the following would be more likely? A random sample of 10 male students having a mean height of 72, or a random sample of 30 male students having a mean height of 72? So the answer is the second one. This is because according to the central limit theorem, once n is greater than or equal to 30, the sampling distribution follows a normal model that accurately, or that, more accurately describes the population. Okay. So this was just an introduction to the central limit theorem. To better understand this, you should now obtain a worksheet and work with your partners in understanding what happens when we do sampling distributions and why does it end up becoming a normal distribution.